Hello, today I will present our paper on weekly supervised co-training with swapping assignments for semantic segmentation. Class activation map, CAM, are widely used to generate pseudo-labels in image-level weekly supervised semantic segmentation task. Traditional CAM is noisy and only shows the discriminative areas, and it is also not robust to input variations. We find that the activation map shows stochastic behavior. To prove this theory, we did oracle experiments and asked the question, what if we use pixel labels to supervise CAM? We did 3 experiments. First, for GT group experiment, we use pixel label directly to supervise CAM. No group is a control group. For comparison, we have NS group, which CAM is guided by random noise. The experiment results show that all group of experiment have perfect classification performance, even if you use random noise to fool the model. But they have quite different quality of CAM. NS group can destroy the CAM, while the GT group can improve the CAM. But in weekly supervised learning, you cannot access the pixel label, so we propose to use segmentation pseudo-labels to substitute the pixel label to guide the CAM. Here is the overview of the purposed model. It contains 2 networks, assignment network and online network. They have the same structure. Assignment network is used to produce pseudo-labels, both CPL and SPL, for training online network. It produces CAM pseudo-labels to supervise segmentation prediction, and it also produces segmentation pseudo-labels to update CAMs. Since the learning targets are swapped, we name this as co-training with swapping assignments. We also introduce a technique that explicitly models the uncertainty. As we use pseudo-labels generated by CAM to train the model, the pseudo-labels are noisy and biased. Some of them are more accurate than the others. The question is, how do we know which pseudo-labels are more reliable? Our answer is to use the confidence information. We find the relation between confidence and accuracy. As shown in the heat map, if the CAM confidence is close to 1 or 0, it shows high accuracy. Based on this finding, we define the perplexity score of a pixel in CAMs and use this perplexity to reweight our loss function. We also introduce a technique called dynamic threshold. In general, a threshold is used to split background and foreground. Previous works usually use a fixed threshold. However, this ignores the dynamics of learning. We find that in most of the cases, the distribution of CAM's confidence satisfies the bimodal distribution. Thus, we propose to use Gaussian mixture model to find the optimal threshold during training. In our CAM, we find some object shows high false positive areas with its surrounding areas. For example, bird with branch, train with railway, boat with sea. We call this coexistence problem. We believe that using the low-level information can help, as low layers in a neural network contain more low-level information. Based on this, we introduce auxiliary CAMs. Here is the comparison of the CAM and the auxiliary CAM. We find that the auxiliary CAM can outperform the CAM in those regions with low perplexity. Based on this, we propose to transfer the knowledge from the auxiliary CAM to CAM. We propose contrastive separation in CAMs. Basically, we mine positive and negative regions according to auxiliary CAM. Then we contrastively separate these regions in CAMs by using influence-seat loss. We demonstrate our method on VOC and CoCO dataset. We achieve state-of-the-art performance, and we also have ablation study to show the effectiveness of the proposed modules. Here are some visual results comparing with other state-of-the-art models. We also did analysis to show the effectiveness of our framework. For more details, please refer to our paper and code.